All right, the next graph for oscillation graphs is velocity. This one's a little different, and they're based off each other, which is why these are going in order. So this velocity one comes off this. And so to synthesize this velocity graph, and so you don't have to memorize as much, I want you to think about what's going to happen as it's oscillating. So we're going to have an exchange between spring energy and kinetic energy. Because at the bottom, it's not going to be moving because it has to change direction, and at the top, it's not going to be moving because it has to change direction. So let's use those to isolate where are we going to have the highest kinetic energy, and that's going to be at the equilibrium point. When those forces are balanced and not causing any acceleration, we're going to have our highest velocity. And then we have to look at which way we're headed. So here, we hit our point of equilibrium at 1/4 t. I know I don't have it labeled, but halfway between 0t and half of t is 1/4 t. So at this equilibrium point, we're going in the positive direction, or our wave is moving from the negative to the positive, and so we're going to have our highest positive kinetic energy. So I'm going to label a point there. Then I want to label this peak here. At any peak or trough of the wave, the oscillation is going to be changing direction. The mass would be changing direction here because it came to the top. It's going to stop momentarily, and then it's going to go back on its way down. So I'm going to draw a little dot on the equilibrium point, or on 0 here, for the velocity, because if we're changing direction, there is a point in time at which we're not moving. And so we have a point at 0. It's headed back down and it hits the equilibrium point. So once again, at this point, we are going to have our highest negative velocity because we are falling down, as this is showing here. We're going from the positive to the negative over time, which means we're moving down, and that's going to be our maximum, or our minimum velocity, the one on the bottom. And so then we can just, at t, once again, we're at a peak or a trough. So if we label all the peaks and troughs as dots, and then we alternate now, we can see the start of the shape of our velocity graph. And so then I'm just going to draw it in here real quick. And that's about the shape of the velocity graph. Now this one is represented by v x equals negative 2 pi f times a times our amplitude, and then times the sine of 2 pi f t. And that's how we get that equation. So once again, to find it, if you know your period, you can flip it over, find your frequency. I didn't talk about this on last one because the amplitude is already in there. But if you wanted to find the max velocity, where are we going to have those max velocities? We're at these points here, at 1/4 t, at 3/4 t. And when we plug those into here, at those t times, it's going to cancel out with this, and this sign is going to fall out to a 1. So if we want our max velocity, or V max, by looking at what's going to happen, we're going to see it's really going to equal 2 pi f times our amplitude. And that's going to give us our maximum velocity. Now this one will be positive. You have the negative sign there to make it negative and all that. But in general, 2 pi times the frequency times the amplitude is going to give you the maximum velocity. And that's just because we're at these points here where we're at a peak or a trough. So that's some things to know about the velocity equation for oscillation.